Hi. In this lecture, let's work out the location of an image formed when light refracts through a spherical surface. So you go from one transparent material to another, but they have different indices of refraction. Say N1 on one side and N2 on the other. So we're going to place an object at distance P in front, and we want to find the location of where the image would be formed, where all the light rays would focus on the other side of that surface. So we have a spherical surface on the front. It will have a radius of curvature r since it's spherical, so it's basically globe or spherically shaped, even though it looks like a circle here. All that really matters is that it's spherically shaped on the surface facing the object where the light rays will enter. On the other side, it could be just continuous, same material of index refraction N2 everywhere. We didn't necessarily have to have the other surface. If we did have the other surface, that forms the basis of a lens. A lens has two refracting surfaces. We're going to start with just one in this lecture to work out the relationship from a single refracting surface. That's the one here on the front. And so the idea is, why would light refract and form an image? Well, that has to do with refraction or Snell's law. So if I send a light ray from the location of the object, it will refract when it enters the material, change angle, and it will focus at some point, which would form an image, and that's what we're trying to solve here. Okay, so for Snell's law and the refraction, we need the normal to the surface. So it entered the surface here, so I show in dashed line here the normal to that surface. That's where Snell's law applies. And to form an image on the right side, I'm going to need the index refraction N2 to be larger than the index refraction N1 on the left side, so that the light ray, which comes in at a particular incident angle here, we'll later label it theta 1, it will change and become smaller when it goes into material of higher index refraction. So this angle on the other side, which I'll call theta 2, will be less. That will cause the light ray to focus in. If it's the other way around, it's going to diverge, and we would not get a real image, we'd get a virtual image. So we're going to choose N2 larger than N1 so that we get a real image. So we have N2 larger than N1. As I said, the distance in front of the lens, sorry, not in front of the surface. I'm getting ahead of myself. I'm using lens. In front of the surface, that object distance is P. The image inside the other material, the other side of the single surface, is the image distance Q, and that's going to be positive for a real image. That convention stays the same as it was for mirrors. The object distance, the image distance is positive for real images. And in this case, for a convex spherical surface, it's also positive when you're talking about refraction. Okay, I'll try to get those straight. Okay, so let's see how we can solve this more quantitatively, just as we've done when we were trying to solve for where the image would form when you have light reflect off a spherical reflecting surface off of a mirror. Let's do the same procedure here for a convex surface of a refracting surface. So it's light, it's transparent. Okay, so I'm going to add a bunch of labels here. As promised, here's theta 1. That's the angle of refraction measured from the normal to the surface. Theta 1 for the light ray entering from medium 1 to medium 2. Here's theta 2, the angle of refraction on the other side of the surface, measured again with respect to the normal to the surface. And it's smaller if I've got index of refraction N2 larger than N1 in that case. So we're going to use Snell's law, which says that N1 sine theta 1 is N2 sine theta 2. And that's how I would solve for the angle theta 2, for example, in terms of theta 1 and in terms of the ratio of the indices of refraction. Okay, but to do so, let's use some of the other angles I've labeled here and other distances to try to work out a relationship that relates, say, the image distance Q to the object distance P. And so let's write down those relations, and we're going to go and pull out some trigonometry here, just as we did with handling the case for spherical mirrors. So here we go. Let's start with, say, the first one, the tangent of alpha. So alpha is this angle on the far left. That's describing the angle relative to the optical axis of the light ray that entered the surface up here at the top, near the top. So this angle is alpha here. The tangent of that angle would be the opposite side over the adjacent side. So the opposite side has height, I'm going to label that h, and that would be perpendicular to the optical axis. And the horizontal distance, or the adjacent distance here, well, that's essentially the object distance in front of the surface. But notice, to get to the perpendicular, you have to go a little bit in. I've labeled that small distance delta. So the tangent of alpha would be h over p plus delta, whatever delta is. Now on the other side of the surface, I've labeled it angle beta here. And beta can be thought of as from another triangle from the light ray that refracted into the medium 2, and then here's the normal to the optical axis, again labeled with height h. The tangent of beta in this, for this angle, would be that height h, the opposite side, over the adjacent side. The adjacent side is essentially length q, what is known as the image distance from the vertex, but I have to subtract that small amount delta to get to that perpendicular, so h over q minus delta. Finally, I've introduced an angle phi. That's the angle measured from the center of the radius of center of curvature of the spherical surface. So that's phi. And here, instead of tangent, let's use sine. So the sine of phi is the opposite side, so that's h, height h, over the hypotenuse in this case. Now what's the hypotenuse? Well, this is coming from the center of the curvature of the sphere, center of the sphere, so that distance is just the radius r. So sine of phi is just h over r. Okay, so there's the trigonometry pulled out. We're going to use these relations to find out relations between p and q. But just as we've done with spherical mirrors, we're going to use the small angle approximation. So small angle approximation, which means all these angles will be small. That's essentially known as paraxial light rays that are very close to the optical axis. We're not going to let alpha and beta and phi be very large. So they're going to be very small angles, so we can do this approximation. Later on in a later lecture, we'll figure out how to handle larger angles. What would the surface shape need to be? But anyway, in that case, when the angles are small, the tangent of an angle is approximately equal to the angle itself. So tan alpha becomes alpha. And this extra amount delta, when we stick very close to the optical axis, we also have that delta approaches 0. So we can ignore the delta denominator, and I just have that alpha becomes h over p. Likewise, beta becomes just h over q. Tangent beta, which was this expression here, just becomes beta goes to h over q. And for phi, well, it turns out that the sine of phi also becomes approximately equal to phi, just like the tangent did. And so phi goes to h over r. So that's what we mean by the small angle approximation. And then one step further, even Snell's law itself, shown here, since sine theta becomes approximately equal to theta, instead of n1 sine theta 1 equals n2 sine theta 2, I just have, more simply, n1 theta 1 equals n2 theta 2. So there you go. All right, so let's put that all together to find that relationship. And how am I going to do that? Well, I'm going to start by working out some relationships. I know if I sum all the angles from along a line segment from one side all the way around to the other side, that's going to add up to 180 degrees or pi radians. So let's start at this top line, this axis here from which we measure the angle of refraction. That's the perpendicular to the surface, right? This dotted line. And I know if I go from here an angle all the way to the other side, that's got to add up to pi radians. So I start here, I go part way, and I get theta 1. So I know, okay, this part of the angle, you know, that one is theta 1 to there. Then I have another part of the angle, let me label it in green, going from the orange line to the dashed line representing the height h. And then there's a last part which I'll show in white, which takes us all the way down to the other side of the line, so we get 180 degrees. Now, those pieces, the theta 1, that's the magenta there, and how did I get the green angle, the one that's shown here, the top one? Well, I know the sum of the angles inside a triangle have to add up to pi radians, or 180 degrees. I know this one down here at the bottom is 90 degrees, or pi over 2. This is alpha, so this has to be pi radians minus those two values to add up to pi. So this is going to be pi radians minus pi over 2 minus alpha. Pi minus pi over 2 is just pi over 2, and so that green angle is just pi over 2 minus alpha. So that's this piece. That's that angle up there. And finally, the white angle that I've, or at least drawn in white here, well, I can think of another triangle in here. Again, it's a right angle, right triangle. So the sum has to add up to pi radians. So this angle indicated in white has to be pi over 2 minus phi. So if I add that pi over 2 plus this pi over 2, I get pi. I have to subtract phi and add phi, so it's just pi. So that's going to work. Can't quite draw white, so we'll draw blue. There you go for that angle, adding up to those three angles here. So there's one relationship I've drawn. Nice thing here is I can cancel the pi's because I have pi on the left, but I have pi over 2 plus pi over 2 on the right, and those cancel. So my relationship gets a little bit simpler. I just have theta 1 minus alpha minus phi equals 0. Or putting the alpha and phi on the other side of the equation, I just have theta 1 as alpha plus phi. So hopefully you see that. Just now working through some algebra after doing the geometry and trigonometry. So we have one relationship here for that angle of incidence theta 1 in terms of alpha and phi. Here was alpha, there was phi. But we're not done. We need some more relationships before we finish this off. So let's pick now let's pick a triangle instead of a line to work that out. Now which triangle am I going to choose here? I want to use the angle beta on the far right. Okay, but I could use the triangle that it forms. If I go up here to the point where light refracted and then drop down that line is labeled h, the height h, this forms a triangle. So the sum of the interior angles has to add up to pi radians, right? So what have I got there? I have this white angle here, which I don't know what that is, except I know I have a right triangle for this interior angle here. Interior triangle, I should say. I have, well, let's see. Actually, what I wanted to say in this case, it's not quite the white, my apologies, it's not quite the white angle. Let's make it, we need another color, so we'll do a goldenrod. We'll make it this angle, sorry, we'll make that angle. So that I can still use my angle beta. I'm going to make the triangle here, but it wasn't that wide angle, it's this goldenrod angle all the way from the vertical line to the orange slanted line. That angle there in golden color is pi over 2 minus beta, because if I have pi over 2 minus beta, add beta gives me pi over 2, add that pi over 2, that has to add up to 180 degrees. Well, that's, well, one way to say it, but I'm just showing the goldenrod angle. I don't really even need the whole triangle. So the goldenrod angle is there, it's pi over 2 minus beta, and I can relate it to theta 2 because I know that white angle, which we did use before, that was confusing me for a moment, that's this pi over 2 minus phi. That's the interior of this triangle, this little triangle inside here. And so that has to add up to pi radians. So I've got pi over 2 minus phi, add phi gives me pi over 2, plus pi over 2 gives me pi. So I know the white one is pi over 2 minus phi. That plus theta 2 has to equal the goldenrod angle. So this is the goldenrod angle here on the left, and I did it in terms of the white angle, which is pi over 2 minus phi, which I've labeled blue, plus theta 2. Anyway, needless to say, there was a relationship there for involves beta. phi and theta 2. But we can try to simplify things now if we followed that. So I've got pi over 2 on both sides, so I can cancel that out. And I just have that theta 2 on one side, right, the right side. I've got minus beta on the left side, but I can add phi, add phi on both sides, and it'll be phi minus beta equals theta 2, and that's the relationship here. Sorry for a little bit of confusion there earlier, but this was the relationship we should end up with for theta 2 now in terms of phi and beta. Okay, so what did I do? We have expressions for theta 1 and theta 2. Why do we want theta 1 and theta 2? Oh, well, we have Snell's law involves theta 1 and theta 2, which got reduced to just n1 theta 1 equals n2 theta 2. So, yeah, why don't we plug into there and see what we get? Because we know those angles, alpha, beta, and phi, involve things like the object distance, the image distance, and the radius of curvature. So we're going to take and plug in now from Snell's law, at least the small angle version of it, these values for theta 1 and theta 2. So I do so, and so here's what we do. So we're going to, from the theta 1 and theta 2, well, from Snell's law, we can solve for theta 2 by just dividing, sorry, let me just do that, dividing each side by n2 up here. So if I do that, theta 2 is just n1 over n2 times theta 1. So theta 2 is n1 over n2, as I shown in the bottom left, times theta 1. What was theta 1? Oh, it was alpha plus phi. So n1 over n2 is alpha plus phi. What does it need to equal? Well, n2 over n2 cancel, it's just theta 2. And what was theta 2? Phi minus beta. So theta 2 is phi minus beta based on this second expression down here. But theta 2 is also equal to n1 over n2 times theta 1, where theta 1 is alpha plus phi, and that's the left side. So I have this relationship here. Well, what can I do? I can multiply both sides of that by index refraction n2. So what I'm going to do is multiply this one by n2 and that one by n2. Put some parentheses around it. Well, let's make that a little bit cleaner. Parentheses around it like that. That will cancel this n2 on that side. So I have n1 alpha 1 plus n1 phi 1 on the left side over here. And on the right side I have n2 phi minus n2 beta. Hopefully you see that. Okay, so now we have that expression. So we can collect some terms. We can put the beta on the left side and move the phi on the right side because there's two phi terms. So I have n1 alpha staying on the left. I've moved minus n2 beta to the right side by adding it, so I have n2 beta on the left now. I had an n2 phi on the right, so it stays. And I'm going to subtract off the n1 phi, so here's minus n1 phi. So here's another way of re-expressing that equation in terms of n1 alpha plus n2 beta is equal to the difference in the index of refraction times the angle phi. Now I can start to plug in my definitions for alpha, beta, and phi in terms of p, q, and r. So if we do that, alpha was h over p, so here's n1 h over p. Beta was h over q, so here's n2 h over q equal n2 minus n1 times phi, and phi was h over r. We see that the height h cancels because it's on every term. And voila, we are basically done. We have this relationship here. n1 over p plus n2 over q is the difference n2 minus n1 over the radius of curvature r. So there you go. A little bit of work there with the trig, geometry, and algebra, but we now have an expression for the relationship between the object distance in front of the refracting surface, the image distance behind it, in terms of the radius of curvature and the various indices of refraction. So that is the formula we're going to need, and we'll use it to plug in for two surfaces as well to solve for thin lenses. Okay, we'll stop there.